All right, folks, so we are going to review the roller coaster energy conservation and transformation practice problems today. Here we have a roller coaster diagram. We know that the 800 kilogram roller coaster starts at rest at point A, which is 15 meters above the ground. Points B and E are 10 meters above the ground, and then points C and D are 5 meters above the ground. We want to assume that there is no friction or air resistance, and we're going to use our trusty 10 joules per kilogram meter as our G unit. Okay? So the first thing that we want to actually do before we look at any of the problems is I'm going to take all the information it gave me and I'm just going to fill in everything that I know. So for example, at point A, I know that A is 15 meters above the ground. I know that the cart has a mass of 800 kilograms. Okay? And I also know that at the very, very top, it starts at rest. So at point A, its velocity is 0 meters per second. Okay? I also know that points B and E are 10 meters above the ground. So at B, I'll put the height is 10 meters. And at E, I'll say the height is also 10 meters. Okay? And finally, C and D are 5 meters above the ground. So I'll say height over here is 5 meters, and then the height at D is also 5 meters. Okay, right, great. So the first question wants us to know, okay, to rank the roller coaster speeds from highest to lowest at each point. If the roller coaster is moving the same speed at more than one point, give both points the same ranking. Explain why you ranked it that way. So if you want to actually try this on your own, we'll come back to your predictions later and see how they fared. All right, but for now, let's identify at what points is the roller coaster speeding up and at what point is the roller coaster slowing down. You've used conservation of energy concepts to explain why you identified it this way. Okay? Well, we know just from our everyday knowledge that when things go down a hill, they tend to speed up, and when they go back up the hill, they tend to slow down. Okay, so we know that, but then we can also frame this in terms of conservation of energy. Remember that mechanical energy is the total of all the kinetic energy in the system and all the potential energy in the system. And we know that if you've got an object at rest and it starts to fall, right, its mechanical energy will not change, okay, but as its potential energy goes down, okay, its kinetic energy is going to have to go back up to compensate for that, right? So whatever we lose in potential, we're going to gain in kinetic. And then let's think about what happens to that energy on the way back up, right? It's going to gain that potential energy again. And as a result, it's going to have to lose that kinetic again in order to balance that out so that we have the exact same mechanical energy at every single point in the system. Okay, so whatever one energy form gains, the other loses, but their totals always stay the same. Okay, and then part number 3 asks us to calculate the total amount of energy in the system. Okay, remember that to find your total energy, again, finding our total kinetic and potential, okay, we have to pick a point, any point, where we can get all of our variables at once. Okay, so we need to find a point on this graph, or I'm sorry, a point on this track where we have the object's mass, its gravitational interaction, the height, as well as its velocity. Okay, and based on the diagram, the only point between A, B, C, D, and E where we know all of those things is going to be at point A, right? Because remember, we have the mass, we know our gravitational constant, we have the height, okay? And because we have the mass, we also have its starting velocity, which is going to be 0, okay? So we can take all that together to figure out what is the total mechanical energy at that point. So let's solve for the potential energy, okay? We're going to take the cart's mass at point A, which is 800 kilograms, and we're going to multiply that by the gravitational constant, which again we are using 10 joules per kilogram meter. And we're going to multiply that finally by the height of the cart at this point, right? The height at point A is 15 meters, okay? So I'm taking all the variables from point A. And when you take 800 times 10 times 15, you should end up with 120,000 joules of energy. Okay, so at point A, our potential energy is equal to 120,000 joules. Now let's figure out the kinetic energy at point A. Well, we actually don't have to do any calculations because we know that at point A, the velocity is 0, right? It's starting from rest. So we know if the velocity is 0, that means our kinetic energy has to be 0. Okay? Kinetic energy is the energy of motion. If you don't have motion, you don't have kinetic energy. So now when we want to figure out, well, what is the total mechanical energy of the system, we're just going to add our potential and kinetic energy values together. So 120 plus 0. Okay? So of course that's going to equal 120 joules. I'm sorry, 120,000 joules. So this here, this mechanical energy, that is the total energy, total amount of energy in that system. Okay? And that's going to be really useful for us if we want to figure out what the varying speeds are going to be at each point along the track.